Good afternoon, ladies and gentlemen, friends, colleagues, and fellows. Welcome to this ATSI Australia's International Space Race webinar session this afternoon. In the middle of National Science Week, ATSI's WA Division and South Australia Northern Territory Division are proud to present to you these very interesting and inspiring seminar sessions. Professor Graham Dandy from University of Adelaide and I will be your host this afternoon. My name is Dongku Zhang, the Chair of ATSI WA Division. I wish to open this session by acknowledging the country. As we meet here, I'd like to first to acknowledge the traditional custodian of the land on which we meet. We pay respect to their elders, past and present, and to any Aboriginal and Torres Strait Islander people who may join us here today. As we share and discuss our own knowledge and practices, we acknowledge the deep knowledge forever embedded in the custodianship of the country. Now, I wish to introduce Professor Graham Dandy, my co-host, to say a few words and to introduce our first speaker. Graham.
Thank you, Tonke. First of all, introduce myself. I'm Graham Dandy. I'm chair of the South Australian and Northern Territory Division of ATSI. And I'd like to also acknowledge the Kaurna people, the traditional custodians of the land where I'm based today. And I'd like to acknowledge their elders past, present, and emerging. And I'd like to add my welcome to everyone who's joining us today for this very topical webinar. We have people from all around Australia. I think it's about 150 people joining, so that's terrific. And it's my pleasure to introduce our first speaker, Catherine Burnell. Catherine is the Assistant Manager of the Chief Technical Office from the Australian Space Agency. She's very well qualified to speak to us. She holds bachelor's degrees in physics and aeronautical and space engineering and a master's degree in astronautics and space engineering. She's worked at NASA, the European Space Agency, and Airbus in Germany. And in her current role, she leads a team to develop the Australia's Space Agency's first roadmaps, which will guide the advancement of the country's space capability over the next decade. She's also responsible for the robotics and automation on Earth and in space strategic priority area, the agency's manager of the Remote Operations, Artificial Intelligence and Control Complex, and she leads the work to scope the Moon to Mars Trailblazer program mission concept. So it's my pleasure to introduce Catherine, who will be speaking about the Australian Space Agency. Thanks, Catherine.
Thank you very much. It's a pleasure to be here today. Hopefully you can all see my screen okay. Here we are. So, it's a real pleasure to be here today and to have the chance to talk to all of you about Australia's capabilities and opportunities in space. Australia, as many of you would be aware, has a long heritage in space, a proud heritage, and one of the longest, in fact, with Australia being the third nation to launch a satellite from its territory in the 60s, our long-standing partnership with NASA on tracking deep space missions, our dish days, if you will, which continue today, and a wealth of experience in managing remote sensing data for various industries in the country. But, despite that great heritage and value, we didn't keep up with the innovation, investment, and opportunity realization taking place around the world in space in recent decades. But this has changed. Space no longer has a giggle factor in Australia, and there is an increasing understanding of what it can do for the country. There is now an incredible energy and momentum, and it's why I was so excited, to relocate back here to Australia after about a decade overseas to proudly work on growing the sector. Working in the institutional and commercial space sector overseas, I've seen the incredible value, the technologies and amazing things that can be done in space when you bring together the right conditions of vision, talent, capital, policy, and perseverance. In Australia, the pace of ingenuity and value creation is accelerating every day, and it's an exciting time to be part of Australia for space. And I'm just going to start now with a video.
3, 2, 1.
From getting to places we once never dreamed of,
We have a liftoff. Liftoff on Apollo 11.
to designing the next generation of satellite communications, we are researching, building and testing the technology that helps Australia take the next step. Our precision manufacturing enables Australians to be part of global supply chains so that we can develop the technology that orbits in space and build the ground infrastructure that supports space activities in our southern skies. The application of these space technologies also helps to keep us safe. During times of bushfires and floods, emergency services use satellite images to understand the bigger picture, mapping areas and pinpointing locations, saving lives in the face of disaster. So now that we know what space technology does for us today, what opportunities does it hold for us tomorrow? The Australian Space Agency, growing and transforming the Australian space industry.
So what opportunities does it hold for us tomorrow? I imagine many of you watched the Virgin Galactic and Blue Origin successful flights, or saw Perseverance landing beautifully on Mars before that. But that's really just the tip of the iceberg of what space does. Because while space can excite and inspire, it has a real and huge impact on the economy in our daily lives, and increasingly so. One analogy I like to use is, when Ernest Shackleton left the port in England to set sail to explore Antarctica, he wasn't the only ship leaving port that day. He might have been the only ship that made the history books that day, or inspired others to get into boat building or exploration, but there were also cargo ships, ships carrying medical supplies, military ships, recreational boats, fishing boats, because the ocean is a place. Space is like the ocean. The industry and its applications also have breadth. Space is a place that is the ultimate high ground. We can select different orbits to be close to Earth or far away from Earth, to cover a lot of ground quickly or hover over a single point. And a high ground allows you to see. From the eye in the sky, we can see phenomena around the world. And what you can see, you can connect. Just like a super high mobile phone tower, we can also connect what's in our line of sight or between satellites and networks without wires. So because of this, space has been used to solve water management challenges, to manage remote industries, to track refugee movements, to monitor our climate, and provide services to other space users. This whole diverse range of applications with completely different market needs. Space is a place to do science that impacts life on Earth. It's a place to manufacture products like long and pure optical fibers. It's a place to kickstart or bootstrap technologies like quantum. It's a place to explore, to progress humanity's efforts in exploration, to stretch what it means to live in extreme conditions and create closed-loop sustainable systems that can be spun back to address terrestrial needs. And it's for these reasons and more that the global space economy has transitioned into what some call Space 4.0, where space is evolving from being a preserve of the governments of a few spacefaring nations to a situation in which there's an increased number of diverse space actors across the world. The foundation of many new companies with quite high private capital deployment, the use of new tech, new approaches, and the convergence of information technology sector into this are forming the basis. So, the old adage to become a millionaire in space, start out as a billionaire, doesn't always hold anymore. It sometimes does, but not always. So it's a really exciting time for space globally, but it's especially so in Australia, because we're in a unique expansion phase of our space capabilities with tremendous opportunity to shape our industry. We can establish ourselves in this new space era, optimized for the opportunities that it brings, rather than having to turn the ship. It's incredible, actually, how fast things have moved just in the last 2 years. Many organisations have now announced their intentions to have their own satellites, many to be developed in Australia. Many Australian startups are already operating satellites in space, in some cases commercially. And we have great R&D that has a high potential to be leveraged towards world-leading opportunities and new gaps. So there's much to be done for Australia to become a global space player. Don't get me wrong, it's not a simple or streamlined path to realising the opportunities in the market today. The Australian Space Agency emerged from this background. Our purpose is written here. It's to transform and grow a globally respected Australian space industry that lifts the broader economy, inspires and improves the lives of Australians, underpinned by strong national and international engagement. Our role is to be the central coordination point for civil space activities in the country. And our top level KPIs are jobs and growth related. Now, this is different from most space agencies around the world who are often science focused. What this affords us, is the ability to concentrate on growing the sector towards a sustainable industry to realise new space market opportunities, as well as more industrialised models to deliver operational space capability to the nation as needed. So our goal is to triple the size of the Australian space sector to 12 billion Australian dollars and create an additional 20,000 new jobs by 2030. That's no small goal. And so to realise it, the government released the Australian Civil Space Strategy in 2019, which sets out a 10-year vision to guide the growth of the whole sector. This strategy identifies 7 areas considered to have the greatest opportunity to serve both national needs and markets of opportunity. These are P&T, Earth observation, communications technologies and services, space situational awareness and debris monitoring, leapfrog R&D, robotics and automation on Earth and in space, and access to space. The rationale for deriving them was that Australia should leverage our strengths rather than reinventing the wheel to try and catch up to some other industries that have had decades and billions of dollars of invest. And that we should also be able to develop capability in areas where there's a sovereign need to do so. And then this is because, leveraging our strengths, especially spinning in from our specialty technology bases and industries like astronomy, energy and resources and remote industries, means we can develop products and services that can compete and contribute value into the international space marketplace. It means that we can make important contributions to international missions that grant us a seat at the table, which then in turn provides us with learning opportunities to accelerate capability in the other SPAs. The strategy calls for the development of roadmaps for each of these individual publications per SPA. And these publications will each be a mechanism to build on the activities to date in that area, to call out the areas of opportunity for industry, and to identify the role Australia could have within that domain in the future. So these roadmaps are under development now. My role at the agency is to project manage across all of these. We've published one so far, the communication technologies and services one, and the others will be released over the coming months. Each of them is developed in close collaboration with the space sector, because it's the prerogative of the entire sector to realise these joint visions and ambitions per roadmap together. For each of these, we have a technical advisory group that includes, the preeminent experts across the country. For the communications one, Sacha, our next speaker, was actually a great contributor as part of that tag. So for a capability to be included on a roadmap, we have really strict criteria. Fulfilling these rests on a strong evidence base. We focus on areas where we can build that sustainable industry, where we play into gaps on the market with the strength. It's important, though, that we also develop the necessary basis for the ecosystem and local supply chains. So we look for these nuggets of niche competitive advantages that we can leverage, and then look at the capabilities around those that the country needs, that the ecosystem needs to underpin them, and then implement them. But the strategic priority areas, the SPAs, don't exist in isolation, despite that they each have their own roadmap developed. They're all interconnected. They're all reliant on cross-cutting technology areas. They're facilitated by non-technical enabling activities, and they may be applied to many cross-cutting services. And so to sort of pictorially explain this, I have this diagram that I call the capability nexus or the roadmaps nexus. Firstly, let's look at the cross-cutting technology areas. These are key technology areas from the broader economy that underpin Australia's future space capability. They were sort of distilled bottom up, actually, when we did all the roadmaps, and they're all bubbling there kind of in second or third order. And I thought it was important to really draw them out. You can probably see by looking at the topics there that there's a really strong relation with the adoption of Industry 4.0 practices to unlock growth. Which is considered as the unfolding fourth industrial revolution of manufacturing and services more broadly. 50 years ago, space paved the way for the ICT industry, and now it's the ICT industry that's setting the pace for the space industry. The dynamism there is far higher than in the traditional space industry. It's driven by short generation cycles of 2 or 3 years, it's highly competitive, and it places innovation pressure in mass markets. Space sector through our activities. For example, space has been identified as a national manufacturing priority through the Modern Manufacturing Initiative. And this should help us to close gaps in our space value chain, which will help us to bring products to market with scale, especially when we close any gaps in the upstream. These facilitators now, these are the ecosystem builders. They're what enables streamlined progress towards realizing the targeted capabilities per SBA. And implementing these, the idea there is that will foster environments conducive to impactful and targeted R&D and to a dynamic and robust commercially focused ecosystem that's a positive ecosystem for new business ventures. We then have our cross-cutting services, and these are the areas of high opportunity and enduring priority for the application of Australian space capability. They each draw upon capabilities spanning more than one SPA. Of course, there's some capabilities that are specific to a space priority area, right? But these are the ones that cross-cut them. Sourcing first and then obtaining ongoing customers for each of these applications is actually really critical for technology capability utilization and realization for all of the SPAs. And, you know, with this diagram, I could take you through each box in an individual presentation. So I'm just going to focus on one today because of its high applicability to a near-term opportunity that the Australian Space Agency has for the sector, which is the Moon to Mars program, and that's exploration services. So different elements of each strategic priority area may, of course, be applied here. But we've identified 3 key areas of priority for exploration services over the coming decade. These are what we call foundation services, health services, and communication services for exploration. Much of the capabilities for these stems from spinning in world-leading approaches from our remote industries in Australia. By virtue of our country's vastness, by necessity, our industries have had to handle already, you know, distance and complex operations in extreme environments with connectivity challenges and finding solutions to have appropriate levels of automation at the edge. So let's look at these each in more detail. So today, in space, sophisticated space facilities like the International Space Station are operated by many nations and are mostly teleoperated. Space robotic missions like rovers have whole control centers per mission working around the clock. Now, this is not commercially sustainable or feasible as activities scale into the future or as they transition to private industry or move beyond low Earth orbit. A key gap to unlock space progress is trusted autonomy, especially for robots to work collaboratively around or with each other and humans. And if we can unlock that, a whole host of new space applications become possible and become interesting. And what we have in Australia already is field robotics with niche capabilities relevant to the space domain, advanced perception, AI, rugged working robots that can work collaboratively and interoperatively. This is recognised, you know, with Australian teams winning DARPA and Amazon challenges. Our resources sector leads the world in remotely operating facilities and autonomous systems in GPS-denied environments with difficult dust, extreme temperatures, and minimal human interaction. Of note is their remote ops capability, remote operations capability for simultaneously managing large complex systems and multiple diverse assets at once, like entire mine sites from thousands of kilometers away. And it does this with high levels of operational uptime, safety, and process efficiency. The technical uniqueness of this stems from sophisticated software that ensures appropriate levels of autonomy and interoperability across all levels of the system architecture. Space doesn't do this yet. We can look to spin this into space to solve one of the key challenges, particularly in lunar activities, which is the near-term application possibility. So to look at how we can spin this in, at the Space Agency, we've coined the term foundation services to mean operational services that support missions to build towards and to maintain a sustained off-Earth presence. These are services for which the application demand is recurrent, continuous, enduring. The scope is things like monitoring and inspection, planning and logistics, civil construction, materials transport, cargo handling, remote maintenance, and so on. And these are distinct from your traditional spacecraft subsystems like power, comms, or life support. And they're necessary for the sustained buildup of space infrastructure. It's our view that Australia could become a key provider of foundation services for exploration missions if we focus it as an activity. This is ambitious for sure, but targeted near-term opportunities in growing lunar surface markets can be explored in parallel with smaller, stepwise, immediate opportunities in in-station cargo handling. And that could position Australia well to future market opportunities in the 2030s and beyond, like on-orbit assembly and manufacture. For exploration health services, Australia has an extensive history in the delivery of telemedicine and remote health services, from the Royal Flying Doctor Service to the Australian Antarctic Division. Exploration activities could present a really important pathway to leverage our expertise in these for space opportunities with high potential that ought to also benefit everyday Australians as we spin back the lessons we learn in space. For example, bone and muscle disorders are a huge issue for astronauts. But at the same time, they cost Australians over $12.5 billion in 2016. So applying new space knowledge and technologies like biomarkers, predictive analytics, and so on could help realise significant cost savings for healthcare providers and users in Australia. We also have strengths in special forms of agriculture, in microdosimetry for detecting radiation exposure in humans and equipment, and light effective shielding for radiation protection. And we have the opportunity to roll these into space and establish a key role in driving health management decision-making and processes, as well as providing commercially viable contributions which enhance human astronaut wellbeing and performance. For exploration communication services, we have solid foundations in comms tech and services already, with burgeoning global capabilities in some niches. Of note is optical ground station developments, which can get high volumes of data down quickly. This will be key for lunar applications, as the optical comms uses lasers, so the signal doesn't overly weaken with distance, but I'm sure you'll hear much more about that in Sacha's presentation. We also have IoT, that is satellite-enabled Internet of Things, which involves remote and distributed sensors in situ connected to satellites. Australian companies are already delivering commercial services using this today for things like detecting water levels in water tanks, so farmers don't have to drive around their farms to test them. These sensors could be deployed into the lunar environment for environmental or asset management purposes. Potentially, they could be the eyes and ears on the ground to realise foundation services or distributed science sensors. For each of these areas, we've discussed these with international partner agencies and done our due diligence, and we're confident Australia has competitive advantages it can bring value to the global ecosystem with. So finally, setting the conditions for the 2030s. The Australian space sector has great potential in all its SPAs to contribute value and realise opportunities if gaps can be overcome to commercialise R&D and scale existing capabilities. The 2030s is when we're going to see the operational implementation of many of our technology strengths come into play. Key trends in that timeframe include, increased dependence on space-derived information and technologies. Addressing global challenges such as climate change are going to call for space to do its part, both for monitoring and for near real-time actionable insights in times of crisis. To support the associated growth in EO, comms, connectivity, and PNT satellites, in-space applications like space services, in-space manufacturing, and commercial stations are expected to take off. We have so much to learn and to do as we push the boundaries of our knowledge to ensure Australia is at the forefront of these space developments and in becoming integrated in Australia's society and economy. For this to happen, space has to be secure, it has to be safe, and it has to be accessible. At the Space Agency, we're working with the sector to support the building of the critical mass and capability investments and ecosystems needed to ensure such sustainable growth and to realise this vision. Our current programs open for applications include the Space Infrastructure Fund and the Moon to Mars Initiative. It's a great time to be in the Australian sector, and I really look forward to the years ahead, working together with many of you in the audience today to realise such ambitions. Thank you.
Thank you, Catherine, for that stimulating presentation. Now, we do have a few minutes for questions, and I neglected to mention, but I did send out something in the chat box, that if you have a question, you can enter it in or we'd ask you to enter it in the Q&A box at the bottom of the screen, on the bottom ribbon. Since I don't see any questions at the moment, that gives me the opportunity to ask a couple of questions. We've got a number of students who are in the audience today. I think some are at high school, a number of probably undergraduate students, maybe postgrad. If students are interested in pursuing a career in the space industry, is there any particular advice you'd have on a path that they could follow, or are there so many opportunities? There's a lot of directions they could go.
I think that it's still challenging to enter the space industry, but the opportunities are growing far more than when I graduated from university in Sydney in 2007. When I graduated, it was go overseas or basically change career. So I went overseas. Today, if you look around, there's a lot of really interesting SMEs and startups, and even some primes now in Australia doing some great work. I'd look at which ones have recently been awarded agency grants and apply, because they're probably ramping up activities and looking for, interns or young staff to help them out. I would recommend people be willing to relocate within Australia or briefly overseas to learn. I mean, there's so much that you have to learn, and often the value you bring isn't so much your technical competence, it's your understanding of the ecosystem and how it ticks initially as you build your capability. So the breadth of knowledge that you can learn by gaining diverse experiences is important. And I would also say that you don't have to feel like you have to do engineering or maths to be involved in space. As you heard, there's medical opportunities. There's also business development. There's entrepreneurship, business leader work that has to be done. There's policy, there's marketing and sales. So I'd say follow your passion and link it to space, and you'll do better than if you try and force yourself into a degree that might not be suited to you just to get into the space sector.
Thank you. And we have a question from Robin King. You're looking at 20,000 new jobs. Have you mapped what disciplines these jobs might be in? Which areas?
Yeah, there's work ongoing in the strategy and policy team here that does, the economic baseline into where space is today and mapping it forward into the future. And they certainly look at the types of jobs that is. I don't have, specific numbers that I can provide you with today, but there'll certainly be jobs, at all levels, in all types in the space sector. When they say 20,000 jobs, it's not just technical jobs, right? It's the supporting functions as well. And in the technical fields, there's a whole host of different types, from technicians and trades to technical experts with postdocs and so on. So yes, it will be a diverse suite of types of jobs there.
Okay, we have time for one more question. We have a question from, I've lost it. Nima De Dushti. Can you please elaborate on the Australian Space Agency interest on infrared focal plane arrays, FPA, for imaging, sensing in shortwave, midwave and longwave? Fairly technical question. Can you handle that one?
I'm not familiar hugely with that sensor. I have experts supporting some of the roadmaps. If we're talking about infrared was it infrared sensors, sorry, for a spacecraft. So I guess there's different types of sensors we look at, right? So there's the Earth observation work that we look at in the Earth observation roadmap, which is certainly mapping the different types of Earth observation sensors. There's ground-based sensors for space situational awareness. as well. We're basically, what we do is we'll look at any technology that we see is having activity in Australia, and we'll assess that against international standards by doing our own work, by using the technical advisory groups and speaking with partner agencies. So my colleagues on whichever roadmap that's relevant to, I'm sure will be doing that, but you're welcome to shoot me an email or the agency an email if you'd like to draw attention to that work, or I'm happy to follow up your question offline to provide a more specific answer.
Okay, now it's time to move on to our next speaker. There are some more questions, and if you have time, Catherine, you might look at those at the Q&A box and answer some online. But thank you very much for quite a stimulating presentation.
Thank you.
And setting the groundwork for our webinar. It's terrific. And so now I'll hand over to Donkey to introduce our second speaker.
Thank you, Graham. What a very interesting talk by Catherine. Now it's my pleasure to introduce my colleague, Dr. Sacha Shadaway. Sacha is a research fellow within UWA's International Space Center in our physics school. He has been working on very interesting technology, has enormous space and also implications. Sacha began his space-related career really from his undergraduate project analyzing NASA's Apollo lunar samples when he was doing undergraduate study at Curtin University. A few years later, 2007, he obtained a PhD from UWA by working on developing advanced LIGO detectors for gravitational wave. During his PhD tenure, he spent 6 months at Caltech in California. And since 2018, he has translated the technology that he had been working on during his PhD and his work with the Square Kilometre Array telescope based in WA, and combining them with advanced optics technology used in cutting-edge optical telescopes. He really, through this work, he became a world leader in the pioneering field of free space optical frequency transfer. Earlier this year, Sacha was named the Australia Space Awards Academic of the Year and the winner of the Overall Excellence Award. Well done, Sacha. Today, Sacha is going to talk about his work on ultra-stable laser links between ground and space. Without further ado, Sacha.
Okay, thank you very much for the wonderful introduction. And thank you for the opportunity to speak to you today. I'm showing here a picture of the West Australian Optical Ground Station, and sort of leading on from Catherine's talk, we plan to use this ground station for communicating with satellites to space and to be part of NASA's moon mission as well. But the topic of my talk today is actually using that same ground station and some of that technology to uncover and search for and discover the true nature of space and time using laser timing links between ground and space. So just a quick outline of my talk. I'll give you a bit of a motivation about the science behind this problem. Then I'll give you a background on what it takes to send these laser links through the atmosphere. It's free space laser links. And then I'll talk about the work we've been doing. Trying to establish the first laser timing link between ground and space. And then I'll finish off with some next step and our future aspirations. But first, I'd like to just acknowledge all of our partners from whom we've received support and funding for this work over the years, and of course, a big thank you also to my group at UWA for obviously helping do all of this work that I'm presenting on today. So going right in. I'm talking about two of the most successful theories of physics: Einstein's general theory of relativity and quantum mechanics. So general relativity describes the fundamental nature of space and time on the larger scales in the universe. It tells us how objects move in space, from the orbits of our planets in our solar system to apples falling from trees right here on Earth. And it also helps us understand how time slows down in the presence of strong gravitational fields. On the other hand, on the right, quantum mechanics describes the nature of space and time on the smaller scales in the universe. It describes the properties of atoms and molecules and their interactions. But quantum mechanics underpins virtually all modern technology, from the transistors found in everyday objects such as computers and smartphones to specialized quantum machines such as the ultra-stable atomic clocks that are used to keep time on board GPS satellites. So these two theories are the most successful laws in physics, and their predictions each accurately describe our observable universe. And every experiment we've taken to date over the last 100 years or so has proved these results exactly as predicted. However, we know there's a big problem. These two theories contradict each other. Quantum mechanics does not include gravity, and the maths used to describe general relativity just stops working at small scales. And for most of the universe, that's okay, because on small scales, gravity is too weak to impact atoms, and on large scales, the weird quantum properties of atoms wash out. But there are some regions in the universe that do have large gravity on small scales. And two examples here are inside the hearts of black holes and in the time shortly after the Big Bang. So we're now at a point where we've reached this chasm in our understanding of how the universe works. And we will need to modify at least one of these theories in order to create a theory of everything, to really truly understand how the universe works. So how do we, what's the best way of looking for this clue to unravel this mystery? So we need an experiment that can explore areas of the universe where the force of gravity interacts with the quantum world. And as I said before, gravity doesn't just make apples fall to the ground, it also slows down time. So a clock on the surface of the Earth actually ticks slower than a clock floating in space. And we call this gravitational time dilation. So we need to measure this gravitational time dilation between two clocks in wildly different gravitational fields. And what we want to do is look for a difference in this gravitational time dilation as predicted by general relativity. And then we'll have that clue. And so I'll start with a bit of an accident. Back in 2014, the European Space Agency launched two of Europe's GPS satellites called Galileo. However, there was a problem with the spacecraft that launched those two satellites. And it turned out the satellites ended in the wrong orbit. They were supposed to be in a round orbit around the Earth to provide their timing signals to the ground, but they ended up in this elliptical orbit. And what that meant is that every 13 or so hours, the satellites came closer to the Earth to experience stronger gravitational field, and then went away and experienced a lighter gravitational field. And it turns out this was the perfect experiment to investigate this time dilation effect. If we looked at the timing signals sent from those satellites, the scientists were able to work out or make it the best yet constraint on this time dilation effect of general relativity, about 2 parts in 10,000, which is an improvement of 5 times over the previous best. Since then, there's an international effort to have a dedicated mission to look at this effect called the Atomic Clock Ensemble in Space. It's a $150 million mission to fly a microwave frequency atomic clock on the International Space Station sometime later this year. Here in the photo at the bottom left is a photo of this clock. And on the right, you can see a section of the International Space Station with some scaffolding on the outside, and that's where this clock will be positioned. So it's, judging by the performance of that clock, it's expected they'll be able to do this gravitational time dilation test to about 3 parts in a million. So about an 8-fold improvement over this previous Galileo result. So, you know, 8-fold, that's not bad. But we're here to see how we can go in the future. And so one of the things to look at is that the microwave clocks in this ACES mission are really outdated technology. So on this figure here in the middle of the page, I'm showing on the y-axis the stability of the clock. So the further down on the y-axis, the more stable the clock is. So the lower, the better. And on the right is the year that the clocks were developed. And you can see these 2 trends. So in the sort of blue teal line is the microwave clocks, and they're still going down and getting a little bit better, but they've kind of stopped. Whereas another technology, optical atomic clocks, are improving much more rapidly. And one thing I want you to take away from this plot is that about right now we're at this 1 part in 10 to the minus 19 of stability. So that's like a 1 with 19 zeros. Sorry, a 0 and then a dot and then 19 zeros in stability. And to put this in a bit of perspective, that's about, if that was a clock running since the age of the universe, it would have only drifted by 1/100th of a second. A bit hard to imagine because no one has a feeling for how old the universe is. The point is that they're extremely stable. But this raises a new problem in that we need, in order to measure the differences between clocks, we need our timing link to be better or just as good or better than those clocks themselves. And here we run into a problem, and that's the turbulence in the atmosphere. So just as in this famous picture here, showing the swirling and twirls in the atmosphere, it's the same reason that stars twinkle when you look up in the night sky. And so if we wanted to send a laser timing signal for that atmosphere, we run into this issue of atmospheric turbulence. And I've written some words here on the screen. They're extremely hard to read because the turbulence is in the way. So what we need is a technology to remove that turbulence and allow us to do this laser timing link science. And that's indeed exactly what we've working on at the University of Western Australia. 2 quick points. That turbulence has 2 effects on our laser beam. So one is it impacts the beam in sort of a crosswise way, so it makes the beam point off target. But it also affects the line of sight, and that changes the timing of the laser beam going from one place to another, and therefore degrades the timing stability, meaning it wouldn't be useful for us in this case. So what we've done is we've come up with a system to suppress this atmospheric turbulence, and we can start with a laser on one side, we send it through the atmosphere, and then detect it at the remote side and pass it on. But as I said, in the atmospheric part, the beam will get disturbed. So what we can do is we can have a mirror at the far end. So where the satellite would be, we reflect some of that signal back and mix it, compare it against the signal that we send out. And then we can measure how that signal is changing hundreds of times per second. And then we can feed that signal back using some electronics and change the timing of the laser signal as it goes out to compensate for that atmospheric turbulence. And here you can see some boxes where that contains that system inside, and then we can take those and move them around. But I said there's also 2 elements. So one is the time of flight, and the other is the pointing in the right direction. And so we've also built these optical terminals that make sure the beam points in the right direction at all times. And again, there's a small adjustments that these make to a mirror to make sure they're always pointing in the same spot. So last year we took that system, we packaged it in boxes, and we went over to France to work with our colleagues at the French Space Agency, and we deployed this link over the air for the first time. you can see a sort of a setup here. These are those systems that I showed earlier. Here's some photos of me. We had to go in winter because in winter, evidently, according to our colleagues, the air is the most stable. It was also a bit uncomfortable for us. You can see me here with a big jacket, gloves, and the hoodie on. My PhD student, on the other hand, didn't seem to mind the winter temperatures at all. But we had a great time, and luckily this was just before COVID hit, and the trip was a big success. So how do we do? Here's a busy plot. I won't go into the details. The point again is that on the y-axis, lower is better, and on the bottom axis, the x-axis, that's for how long we measure. And so you can see here, after a few seconds of measurement, a few minutes of measurement, our ability to transfer that timing signal is at that same 10 to the minus 19 level. So giving us the ability to have a system that's at the same level as those clocks. So that was a great start, but we wanted to do a bit better. We wanted to go over a link that had the same amount of turbulence as a link going all the way to space. And so when we came back to Australia, we set up the same system between two buildings in Perth, and we sent those timing signals from one to the other and then back. And importantly, we measured that the turbulence on this link was the same as going all the way to space. So one question might be, how can the turbulence over a relatively short distance of a few kilometers be the same as going to space? Well, it turns out most of the air is very close to the ground, and so therefore most of the turbulence is close to the ground. So if you go up only a few hundred meters, a few kilometers, you're above most of the turbulence. And so this was a really good demonstration. Just to give you an idea what this looked like. Here's our experimental setup, and you can see it's quite a long way to the next building. And critically, we're able to improve the systems that we took to France with us and have even better results this time around. So now, same sort of plot, lower is better, and you can see here that our system now is performing more than 10 times better than those stabilities of those clocks, allowing us to be ready for those measurements. So that's all really great. We've got the right technology, but in the end, we need to shoot up into space. There's only so much point going sideways. So for this, we're commissioning the West Australian Optical Ground Station, and that's going to give us the ability to shoot straight up. And this is going to be located on the roof of our building at the University of Western Australia. So up to now, we've been commissioning all the systems that work with that. So here you can see our telescope. It's a time-lapse movie sped up 30 times, where that telescope is pretending to acquire signals from a satellite and then track that satellite as it moves across the sky, just as we would need to do in the future. We've got a control room already, and we've got some custom software that allows us to set the telescope up in just the right way to follow those satellites and get those laser signals back. And here you can really see the telescope working exactly as intended. So my colleague here is holding a model of a satellite, and it's sending a laser signal to the telescope. And as he moves that satellite up and down, you can see the telescope is locked onto that laser signal and tracking it exactly as it should be. Again, that's all great. At the moment, we're sort of in the lab space. We're just commissioning this, but just this week, just this week, we're installing that telescope on the roof of the building, and you can see here the cranes that we're going to be using to move that telescope and have it ready. But of course, it's a big jump to go straight from this laboratory environment to shooting lasers to satellites. So we're going to take some intermediate steps first. We've got ourselves a nice drone. We can put an optical payload on that drone. You can see here in the video, and practice establishing those timing links to that drone. And that drone might be able to fly up to a kilometer or so in the sky. Once we can do that, we can move on to an aircraft, which might be able to fly at 5 or 10 kilometers in altitude. And again, once that system's working, we're ready to really move on into space. So then our next steps and our future aspirations are to provide this laser link technology for this next generation optical frequency gravitational time dilation mission, so that we can further our understanding of the universe. This will look very similar to a proposal that I was involved with in 2014, so a few years ago, called STE Quest. And that was predicted to perform about 30 times better than the ACES mission that I talked about before. So quite a significant improvement. At the time it wasn't selected, it was found that those optical clocks just weren't technologically ready enough to launch into space. But since that time, colleagues in Japan and colleagues in Germany have started to develop clocks that are more miniaturized, that are robust, that are starting to become ready to launch into space. And when they are ready to do so, we want to have this Australian technology be ready to be able to support those missions. But in the meantime, there's plenty that we can do with that technology. So more in the near term, we want to demonstrate this next generation satellite laser ranging system. And so that's going to help us for improving global position navigation and timing, which is another focus area of the space agency. We want to develop ultra high speed space to ground optical communication. And again, you heard a little bit about that already, and quantum secured information. And then finally, we want to use our ground station to provide the optical communication support for NASA's upcoming moon missions and beyond. With that, thank you very much for your attention.
Sacha, thank you very much. I just moments ago had a bit technical difficulties. I had to quit and rejoin. My apologies. We do have one question in the QA from Martin Thomas. The question is actually addressed to Catherine. A fascinating presentation. Does the Australia Space Agency offer opportunities for undergrads to work with ASA in the university vacation with a view to join Australia Space Agency upon graduation?
Thank you for the question. The Australian Space Agency sits within DISA, which is a government department, and DISA has, a graduate program. I think it also has internship programs. We don't have a space agency specific program though, but I encourage you to look at that if you're interested in working with us. I know we just hired a graduate on a short-term, 6-month contract, I think it was, to help us because she had specific skill sets we're after. Across the sector, a lot of our academics, our researchers, our startups and SMEs do have internship and graduate programs. Sometimes these are advertised, sometimes they're just happy to accept cold applications. So I wouldn't be shy about applying to those. Space is a small industry. It's really important to network. I know it's difficult with COVID, but attending events online is a starter at university and so on as well. So yeah, network and apply everywhere would be my recommendation. I think some overseas agencies and companies are even offering virtual internships. I know you don't quite get the same experience, but it's still a massive foot in the door.
Thank you, Catherine. I'm alluded to a question from Andrew Smith for Sacha, but I cannot see the question. I have a question from Daniel Ricardo. Hi, Sacha, great talk. Wondering if these systems would be applicable to ground orbit communication systems on other planets, i.e. Mars, with different atmosphere properties. Sacha.
Yeah, great question. Absolutely. The key is that it's able to mitigate the atmospheric turbulence. Having said that, I think because Mars has a much less dense atmosphere, I think the problems that we need to overcome in Earth's atmosphere are much greater. So if anything, the challenges on Mars will be much simpler. And really the key is here on Earth. That's really where for communications, For instance, that's really where the main driver is. That's where thousands of constellation satellites are going up, and more data is generated, and we need to get that data to the ground, to Earth, more readily. Donkey, I can see those Q&A questions if you'd like me to go through those.
There is can you see Andrew Smith's question?
I can. So yeah, there's a question from Andrew and a similar one from David Cohen. And the question is, wouldn't the ground station be better based on a mountain? And it's absolutely true. It's the reason why the world's best optical telescopes are on very high on mountains in the best sites in the world. So we can definitely do that. Here we have an opportunity to test this technology in our setting. It's very easy for us to get to. It also needs to be where those optical clocks are. So again, having that in a university environment with our research labs is a good spot. Having said that, we're interested in developing the technology, and if we're the world leader in this technology, then if such a system, such an experiment happens around the world, then there'll be multiple of these ground stations located. Some might be on mountains, and some might need to be located in cities where those clocks are. So if we can make that best technology that we can and have it work in most conditions, then I think we're in the best spot.
Thanks. Sacha, there's a question from Cameron Porter. Can you see that?
Yes, so it says, does attenuation limit laser communication to lower orbits, or is it possible to go to geostationary orbit and beyond? It certainly does become more challenging the further away you go from Earth. Many of the communication satellites that are coming up are relatively close to Earth, within 500 kilometers. And they're let's say the easiest ones to target for having a relatively small telescope. Having said that, our ground station, which has an aperture of about 70 centimeters, it's very similar to other ground stations, like one that's being developed in the Australian National University, for instance, colleagues of ours. They're found to be good enough to also be able to do a link all the way between Earth and the Moon with special equipment. So if you have that, yes, you can go anywhere from low Earth orbit to geostationary orbit and then all the way to Moon. If you want to do Mars, you probably need something a bit bigger than this.
Sacha, there's also a question from Rowan Gilmore. Can you see that one? It
is. It says, Rowan says, I understand space to ground optical communications is less subject to turbulence than ground to space. Is it true? And if so, why is infrared non-reciprocal? It's a really good question. The sort of thing that I might follow up on with you. It's basically, it is reciprocal, but I guess as you're closer to the ground, you have certain effects that happen, and as your laser beam goes up, and then as it reflects down, the telescope is already pointing in a different direction as the satellite moves overhead, and so there is that non-reciprocity that comes into play because you have this effect of moving objects and at time of flight instances as well. And also the beam from space, starts small and then spreads out. Whereas, so it's a big beam by the time it gets to the ground, whereas when you launch, you start small and then it's big at the top. So you do sample different amounts or different spatial scales of turbulence that way. So it does change.
We have a question from Ramprakash asking what kind of laser is used for your application and how powerful it is.
At the moment, we are working with in the optical communications range of wavelengths, so 15 to 50 nanometers. It's the same technology that's used on the internet, on optical fibers. And it seems as though most of the free space communications technology is going along those lines. It's a safer, in terms of eye safe, it's a safer technology to use than some other laser technologies. And it's actually relatively not powerful for the testing that we're doing. So it's at the moment it's completely eye safe. and it's invisible. So it's safe to operate while there's spacecraft and aircraft and other things flying around.
Sacha, I have a question for you. If we use the laser communication technology to detect, say, space junks or any objects, maybe any junks in the space, what is the size resolution you could identify?
Yeah, it's a bit different sort of technology than what we're talking about, I think, in this case. I think there's imaging you can do with a standard camera, and that gets you down to a certain size. And yes, you can also reflect laser signals or radio signals off space junk. In this case, because we are using low-powered signals, it's not really suitable for this. But there are, again, our colleagues in Canberra are working on some really exciting projects where they use extremely high-powered lasers to try to not only sense where that space junk is, but then actually to put pressure on it and deorbit it and clean up the environment in space.
Thank you. We have a question from Mark Ding for you, Sacha. How is spacecraft laser reflector aligned accurately? Corner reflector? Question mark.
Yes. So for the, initial experiments, or where you're trying to find localize the position of spacecraft, then there's a corner of many spacecraft come with corner reflectors, and they will bounce the light directly back. For these advanced timing links that we're talking about, we would actually receive the signal at the spacecraft, and then there'll be another laser that is locked to that incoming signal and then shoot that signal back. So it actually, the reflection, let's say, occurs within the optics and electronics that are in a small segment, a small payload that exists on the spacecraft itself.
I see. Thank you, Sacha. I think we have run out of time, and if there are any more questions from the audience, obviously you can reach out to our speakers and our panelists, and ETSI will do the best to handle your question and get your questions answered. I'd like to take this opportunity to thank our speakers, Catherine and Sacha, for your wonderful presentation. And I also like to acknowledge our audience across the country. We of about 150 participants counted. Literally every state and territory is represented in the audience. That just illustrates, along with the overtiming, illustrates the talks have sparked enormous interest among our science enthusiasts and space enthusiasts. Graham, thank you very much for co-hosting, and I'll leave it to you to have the final say.
Well, thank you, Donkey. I can't really add any more to what you've said. We had two fascinating presentations with a different, complementary presentations, really. I think Catherine gave a very interesting overview of the Space Agency and the mapping of Australian space capabilities. And there's really so many different skills going to be required in the space industry and areas which we're very strong, Australia is very strong in. And Sacha gave a more technical presentation, starting off with the laws of physics, which is always very interesting to those of us who studied science, and talking about the optical atomic clocks with amazing accuracy, which was quite fascinating, and optical communications in space, which I think is a fascinating area. So two terrific talks. Thank you very much to both speakers, and thank you to the audience. We've had a great audience and terrific number of questions. So thank you, everyone, and keep your eyes open, because we are planning further webinars, joint webinars between South Australia and Western Australia on a variety of topics. So thank you very much, and good afternoon to everyone.
Thank you. Good evening.
Thanks all.
Thank you very much for your time.